Do they have a loss?
No.
So they're still on. Whoever was talking on the radio was speaking live.
Yeah, they played Western. They played Western.
Yes, SFU's.
They won. 12:30. He's telling me they can't move on for that.
I was, after all, singing earlier to go ahead and kiss me. All right. So I want to go back briefly and touch. Yes, sir.
Okay. So that email you sent yesterday, was that for this class or for the
That
other
was for
class?
this class. Yes, I've already been accosted multiple times for not specifying that it was thermodynamic, or that it was. Oh no, it was thermodynamic. Yeah, it was thermodynamic.
Yeah, like.
But I've already been accosted several times for not specifying what class it was.
I'm not condemning you. I'm just genuinely curious because that really
No,
helps
actually,
in these studies.
Lindsay accosted me. Lindsay was much more aggressive than Jesse was.
Okay.
So yes, that was for thermodynamics. So thermodynamics, we got
I
to.
can't say too
So
much.
for those in thermodynamics, be prepared to give an answer. For the hope that lies inside you. No, for whether we're going to do the exam split Monday, Wednesday, or just do it on 2 hours outside of class. But we'll talk about that on Friday. Okay. So I want to go back and revisit a little more detail. I kind of brushed through a couple things last time, and I want to make sure you understand. The first was the effect of cracks. I think it was Colin that asked about the cracks, if I'm not mistaken. And now he's not here to find out a more detailed answer. His loss. All right, so let's say we have a crack in the material. I'm zooming in here, right? So if this is a crack in a brittle, especially in a brittle material, this is a very small crack. Right? If I had a big long crack in a piece of glass or something, it wouldn't be either. It would be appear much narrower, right, in proportion. So there are two characteristic dimensions here: C, which is the crack length, the length from the surface to the tip of the crack, and then if I approximate a circle out here at the end, it has a radius rho. Okay.
Is that like the circle parallel to the cross section?
Diagram in a sugar way.
Because I can't.
This is a circle, so this is assumed to be running infinitely into the wall. Okay.
I'm sorry, I'm having a hard time looking at that in a mature college way.
Grow up.
He also left first.
Okay, so first of all, I think that from my experience, a mature college way is actually an
Too
oxymoron.
loud. A mature college way is too loud.
Alright, I'm having a hard time with that way.
Okay. Anyway, that's the crack tip radius of curvature down there. And I said that the maximum stress experienced in the chunk of material was approximately equal to 2 times the applied stress times the square root of C over rho. So in other words, if I zoom out on this, I've got some sample, some brittle sample that I'm pulling on. And it has a little crack here, right? There's some kind of a nick on the side. So take this, and zoom it out, and I get that. So sigma is the stress that's being applied macroscopically to the whole sample. So yes.
Would it work if we used the S instead of sigma, the S stress?
Yeah, see, there you go.
It works both ways?
Yeah, but this is what I told you. I'll end up using sigma for engineering stress, even though typically most of the time we're using. So this is actually sigma. Okay, this is actually sigma.
But you could also use engineering stress.
But yeah.
Okay.
Because at any instant in time, the difference between them is just the difference in the cross-sectional area. Yes. And this is before yield or anything, so there's not been any deformation.
What's the sigma that doesn't have a slip strip?
That's the applied stress. That's this. Macroscopic applied stress. That's the, that's the force pulling here divided by the cross-sectional area of my sample.
So the maximum stress at which it will.
The maximum stress is the stress at that location right there.
Oh, okay. It's not like a failure stress or something. It's like
That's the stress that's being applied to the crack tip when I apply this nominal stress to the whole thing. So this relationship is a stress concentration. It concentrates the stress, right? Because generally speaking, C is always going to be bigger than rho if it's a crack. Right? The length of the crack is going to be bigger than the crack tip radius of curvature. And so this is going to be a number bigger than 1. And the approximation applies because of the fact that it's a tight crack. If I took a big chunk of sample and instead, this was my sample, and instead I cut out a piece like this, right, out of my otherwise straight piece, I wouldn't use this approach because where here rho is bigger than C. Right? This is I can do that, macroscopically. I don't have to do cracking. There's no real stress concentration.
Wouldn't that be a dent instead of a crack?
And that would be a dent instead of a crack, yes. So it only applies to cracks, not dents.
Can you always approximate a crack as having a radius there?
Right. So even if it is an atomically, what's called an atomically sharp crack. Okay, so meaning there is, I can get down to the atom. I've got a silicon, an oxygen, and a silicon at the tip of that crack, right? Where the bonds that would have been to an oxygen over here have been broken. That would still have a radius, which is essentially the silicon-oxygen bond dimension.
wow.
Okay, and that's a really small number, which means if I have an atomically sharp crack, the stress at that crack is enormous.
So you want a less sharp crack, basically.
Right, you want a less sharp crack if you want the thing to be able to endure.
What if there's a crack? What if there's a crack that branches off of that one crack that you drawn down? Like a crack that goes like up, down.
Or down?
Yeah.
So then, so there would be a different stress state. Right? So if there's a crack going this way, right, there would be a different stress state at the tip of that crack. Because I'm not pulling that crack apart. Right, I'm pulling it in the vertical direction here. So if this crack grew into a crack up and a crack down, then effectively what I've done is I've dramatically increased the radius, crack tip radius of curvature.
What if it's not at the tip though? What if it's far way down?
Well, the tip is all I care about.
Well, what I'm saying is, what if there's a crack? Okay, so what if there's a crack in the middle that comes up at the top, and
Sense
then
of going
that
down a
cracks?
rabbit hole.
No, it cracks up and then it cracks over. So you have a second.
So I have another crack up here doing this.
Yeah.
Well then, whichever one's longer and whichever one's sharper is the one I care about.
Okay.
Okay? Because if this is truly a crack growing up like that, then this thing doesn't really care whether this chunk of stuff is that, to what extent this chunk of stuff is, where that crack came from. That's no different than this out here.
Okay.
See what I'm saying?
Is that theta max approximately equal to?
Sigma
or-
max.
Sorry. Sigma max approximately.
Yeah, that's an
equal or
approximation.
proportional?
That's not an exact relationship.
Okay, but it's not just, it's more than just proportional. It's actually.
Right, proportional to would be an alpha, not an
Approximately
approximate.
an alpha.
This,
I don't actually draw an alpha, I draw something.
that's what it's supposed to be. That's what it's supposed to be wrong. Anyway, all right, so does everybody get this, right? C is longer than rho, so C is a lot longer. If it's an atomically sharp crack, you have huge concentrations of stress. So, if you want to relieve the stress and keep the thing from propagating, you either have to polish away the crack, right? So we get C small, or you have to blunt the crack. So in, this is what I was talking about in class, in cast iron, which is a brittle material, well, some cast iron, there's ductile cast iron too, but most generic cast iron, like a cast iron stove, is made of something that's pretty brittle. Anybody ever try to clean a, remove a cast iron tub from an old house?
Yeah.
How do you do it? You break it up with a sledgehammer, right? It's brittle, you can crack it. An old cast iron tub is broken apart with a sledgehammer, and then you take it out in pieces. Because it's brittle, and you can crack it and break it apart. So in cast iron stoves, if they would get a crack back in the day, you know, because they would get heated, they get a lot of thermal stress from a cast iron stove, you have a wood fire or coal fire inside, especially in the wintertime. You can get cracks, so if you've got a cast iron stove, and this is just going to become a big potbelly stove here, I have no idea what it looks like. All right. There's a crack growing in from the side. They would drill a hole at the end of the crack. The purpose of drilling the hole is to increase row so that you could reduce the stress and keep the crack from growing.
So you're just like, kind of like come in from, it's like, I mean, I'm assuming like it's curved, you just kind of come in from this curve and do it, or you just come along.
So this is really a shell, right? It's an old cast iron stove is a shell. So you're drilling a hole through the shell.
Okay, so you come in like along the crack then?
No.
Or- No.
No.
So you come from.
This is the crack,
Perpendicular.
and here's the hole.
Okay. Yeah, so you would come in from like.
I don't know what you're doing
side.
around the corner.
Okay.
I'm not driving around the pot to go.
If
I'm
it's
just drilling a hole, man. I'm just
circular-
drilling a hole.
I'm thinking like a circular cast iron thing, like.
We're not going to get anywhere today.
It's not a big deal.
You're right, it's not a big deal. Let's move on. All right. And that's why if you're, the example you used in your potato chip bag, if your potato chip bag starts to tear, you know what I'm talking about? You have a, you know, you have a large bag, you want to keep it so fresh, but it starts to tear, you just simply round out the, you tear it into a little circle, tear a little circle at the bottom, and then it won't tear anymore because you no longer have a sharp crack. Okay? So.
All makes sense now.
Yeah, right.
Can I go get my degree?
Can I go get my lunch?
Okay. All right, the other thing that I talked about last time that I didn't feel like I gave good enough justice to was the last few bits. We talked about tensile tests, tensile deformation, and then shear deformation. I drew the little thing, kind of like a deck of cards that shear off to the side, right? But I said for ceramics, you can't really do a tensile test. I can't take a piece of glass and pull on it like that, really, because I'd have to grab hold of the glass and I'd crack the glass trying to hold on to it, right? I can do it sometimes with glass fibers, but I mentioned a modulus of rupture test, which is done in 3-point bend. So I apply a force down F here, so then there's a commensurate force F over 2 on each side, because the problem is symmetric. And there's a separation between these two of L. And then the beam, if I look at it in cross section, has a width B and a height H. Right, this is the side of the end view. And so what you measure for this with a ceramic material, you want to know how strong a ceramic is. Now generally, as I mentioned when I did the tensile test, if you actually did a tensile test on a ceramic, it would do this, and then it would just sort of break. Right? Because there's not a lot of plasticity in a ceramic material. It's brittle, it doesn't deform. And so all we really care about is this one breaking stress. We typically don't care so much about yield stress, tensile stress. They're all kind of the same thing because it all happens about the same point. So with a ceramic material, since we can't really tensile test it very effectively, we do this, we apply this force and wait for it to break. Because what's going to happen is somewhere along the line I'm going to get a crack to grow here and it's going to go right through there. I'm going to start on the bottom surface where I have the most tensile stress. You can kind of see that I'm bending it so that I'm pulling the bottom part apart, while at the same time I squeeze the top together. And so I'm going to get a crack that grows from the bottom. And I measure modulus of rupture, which is 3FL over 2BH squared. That's the characteristic. So that's sort of like the ultimate tensile strength. The equivalent of a flexure strength. It tells you how strong the thing is. Where F in this equation is the force at which it cracks, at which it breaks. So I load it up like that in 3-point bend. It's a 3-point bend because we have 3 points of contact when you bend.
So L is between
the two contact points. So I load it up in 3-point bend until it breaks, and I measure the force at which it breaks, and I use that to calculate a modulus of rupture. So the larger the force, right, the larger the modulus of rupture. Similarly, if I have a particular sample, and if I increase L for a particular kind of material, then it's going to take less force to break it. Right? The further L is apart, the less force it's going to take to cause that thing to break in the center. Because the modulus of rupture then is a characteristic of that material. Okay? So that's what modulus of rupture is. And the other thing I gave you the flexural modulus. Did I write this on the board?
I don't think you wrote either of those on the board.
Okay. I mentioned it, I think, by name. L cubed M over 4 B H cubed. The flexural test is used oftentimes for polymeric materials, where they behave differently in tension than they do in compression. So everything up to this point I've been talking about tensile performance, right? So the stress strain curve in tension, something like that, right? It turns out that for most materials, metals and ceramics, if I went to a compressive stress, so I loaded it, in other words, I squeezed it instead of pulling on it, so I'm going down in a negative sigma, at least up to the point of yield, it would behave in a mirror fashion. Okay. When I get out here toward this area, it doesn't necessarily behave exactly the same, but in the center area, it's sort of it's symmetrical about the origin. Compression and tension behave the same. For polymers, that is not the case.
What is that for? That they behave?
So that would be like metal or ceramic, and if I did it for the ceramic material, it would be kind of the same. Okay. Metals and ceramics are pretty much symmetrical, polymers not so much. And we'll talk more about why that is, but it's related to the way the polymers are structured. Yes.
What is in your E-flex?
I'll get to that in a second.
Then why will it always break on the tensile side? if you're pressing
So
down?
this is a ceramic. The ceramic will always break on the tensile side because of this. There's always some, even if it's microscopic discontinuity, that creates a crack, right? So at this point, I'm pulling that crack apart, I'm accentuating the tensile stress. If I close the crack, I don't have a concentration. The concentration only occurs in tension.
So if you just like pressed on that glass, it would take the same amount of force just to crack it, right? Like if you just had like two.
Well, that's what I said. Once you get out into the deformation section,
Okay.
you know, but if you just sort of ignore this and say that there is no deformation in the glass, it would roughly take the same amount of stress to crack it in compression than it would to pull it apart.
So that's basically like it's just sitting on a hard surface, just hit it.
Well, yeah, hopefully you squeeze it, but you don't hit it. Because of an impulse kind of thing, yeah.
What exactly is the MOR and the E-flex? Like what are they?
So the modulus of rupture is basically provides a measure of the strength of a ceramic or a brittle material. So instead of using a yield strength, right, this is a yield strength, or an ultimate tensile strength, which are derived from a tensile test, we use the modulus of rupture as a measure of strength, and they scale in proportion. So a ceramic that has a high tensile strength, if we could actually measure it that way, would also have an equally high modulus of rupture.
So E-flex is.
So flexural, so E-flex is generated the same way. Okay. But instead of breaking it, we're trying to get a modulus. right? E is an elastic modulus.
Oh,
We're not breaking it.
so it's the slope of that.
So it's the slope of the, in this case, since we don't really have a stress strain curve, we just have a force displacement curve, right? So it will behave somewhat similarly, and M is that slope there. M is the slope at the beginning.
Then E is not slope.
Yes, it's units of slope. It has, should have, is that B squared? It should have units of force per unit area. Yes, that's right, that's right. This is right now, because M is going to be a force per unit length. And this is going to be, everything else is in per unit length, so I end up with force per unit area.
And so
The units are
E
mine.
would be used to calculate what kind of thing?
The elasticity of a polymer.
So is that the same kind of elasticity as?
It's
like
the same
sigma
kind of,
equals
it's the same
E?
kind of thing. It compares to the elastic modulus over here. And that slope is E.
Yeah.
So over here, we're doing, the reason we're doing it is because the flexural test is just, you have both compression and tension happening at the same time. Compression on the top half and tension on the bottom half. So this measures the aggregate compression and tension behavior of the polymer because it's different. The polymer that isn't symmetric about the origin. Polymer has different behavior in tension than it has in compression. Okay? And again, that relates to, I think we'll talk about that at some point when we talk about polymers in greater detail. But that's because when you pull on a polymer, you're actually aligning molecules. Right? You're changing the molecular, the atomic alignment when you pull on it. Whereas when you push on it, you're not really changing.
So E flex is for polymers and R is for.
This is primarily used for polymers. Although anytime you do this, you could also do a flexural modulus for ceramic material if you wanted to. Okay?
So what is the?
This is just the modulus when you're using this system to measure it. And the reason you use this system for measuring polymers is because of the difference between tension and compression. Okay. But you could use this for metals as well. I mean, so I just told you something slightly different about the material.
Are you explaining what it is, or?
M is the slope of the load displacement
Okay,
curve.
okay.
Yes.
So in that case, polymers and ceramics behave similarly when it comes to tensile?
No, it's not that they behave similarly. It's just that they are both things that, for for different reasons, you typically don't want to examine just in a tensile test.
Okay.
Ceramics, because it's really hard to grab hold of them and pull them in a tensile test. It's a lot easier to do this. And polymers, because they behave differently in tension than they do in compression.
But we still use both of the moduluses for ceramics and polymers? Or is,
Both of these characteristics?
yeah.
So this is you're only used for ceramics. You
Okay.
generally aren't going
And that one's
to, you're not
just
going to bend polymers unless it's a brittle polymer, like a piece of hard plastic that would fracture.
Yeah.
You might use the modulus of rupture. This is just exclusively used for ceramic, for brittle materials,
Okay.
where we're actually breaking it and where it's the breaking point that really matters to us. Okay.
The displacement is the displacement of the bottom from where it started, when F equals 0?
D,
Yeah.
yes, it's the force versus the displacement of this beam. And we only care about the slope here at the beginning because it bends. Okay, any other questions about those? I just want to make sure I went into a little more detail. I don't know if I have homework problems that cover these in that detail or not, but I want to make sure that I can cover them because I kind of breezed by them last time. All right. So let's talk about how those macroscopic properties correlate with the microscopic structure that we've already talked about. And in particular, we're going to talk about how it works in metals because that's where most of our time and energy is going to be focused. Okay. So, let me draw out the BCC crystal, unit cell. Okay. Now we've already talked about the fact that we talked about close packed planes. Why'd you guys switch? Trying to be funny? Apparently we are. I don't know.
They get along better than they do.
Oh, okay. Clayton blowing menthol on you again? Okay.
Not yet.
Anyway,
Sounds dangerous.
so we already talked about the fact that we have close packed plane. Remember talking about close packed planes and close packed directions, all that? And we said that the distance, the closer packed the planes were, the further apart they were. Right, so in other words, I think I used the example with my fingers, right? If I spread my fingers apart so that they're not very closely packed together, then they can interlock and the planes will be very close together. But then I'll have to move them quite a bit to move those planes past each other. Whereas if my fingers are very tightly spaced together, then they're further apart, but then they slide across each other more easily. See what I'm talking about? Spread them apart, they're locked more, and it takes more energy to get them to move. Put them together, they slide more readily, and they're further apart. Okay? So, we are primarily interested in these crystals in those close packed planes. The planes where everything, the atoms are really tight together, so that the planes themselves are further apart in order to allow them to slide across one another easily. Because when we deform something, we only care about sort of the weakest link. Right? If we're going to deform a crystal, we only care about where it's going to deform, because the first thing the first mechanism by which it's going to deform is probably going to be the mechanism that's going to completely deform. Right? If it takes 6 joules of energy to cause one deformation and 10 joules to cause another, then it's going to deform in the 6 joule way, because it's a lot easier to get that to happen. So the close packed plane in BCC is this plane. That is the plane that has the highest density of atoms per unit area. Does that make sense? You see that? Okay. So the close packed plane is the 110 plane. Remember the designation, family of planes is squiggle brackets. And we find the plane's orientation by picking an origin not in the plane, find the intercepts, invert them, clear the fractions. Or alternatively, you can find the plane because you know that it's direct, the 110 direction is perpendicular to the 110 plane. The 110 direction is going from the back corner to this corner, right? It goes 1 in the x, 1 in the y, 0 in the z. So that direction is perpendicular to that red plane. You see that? Okay. So the 110 plane is the closed packed plane. The 111 direction is the closed packed direction. That is, the 111 is the direction in which the atoms touch each other. We use a hard sphere model for the atoms. This corner atom touches the center one, which touches that. Right, we've done that several times, several different things. BCC, we know that the body diagonal of BCC is 4R. Okay. So the 110 close packed plane and the 111 close packed direction work together to be the easiest way to deform a lattice. And so if I want to make one of those dislocations move, I'm going to want to make that dislocation move in the 111 direction along the 110 plane. So in my structure, right, this was my thing, and then kind of did this. And something like that. That was kind of the general structure. So what that says is that this direction is the 111 direction in BCC. And this plane on which that thing is sliding is the 110 plane, or family plane. It's a 110 plane and a 111 direction. So if you look at the picture here, you see that's the 110 plane. The 111 direction in that plane is this body diagonal. Or it could be this body diagonal. Right? I could deform that along that plane. I could deform it in that direction or in that direction with equal amount of energy or force or whatever it is. Right? The work necessary to deform it in that direction or that direction are the same. Everybody see that? So there are two of these per close packed plane. There are two close packed directions per close packed plane. And then in the unit cell, there are actually 6 close packed planes. That's 1. You see 1. Here's 2. See how that's a separate plane? And how those two basically make an X on that top face. There are also 2 that make an X on this face. Right, which would be that one. Oops, didn't draw that very well. Right, and then this one. We see those. And then similarly, there would be 2 on this face. So there are basically 2 per face. And they're redundant, the top face and the bottom face are the same.
This is specific to BCC.
This is specific to BCC. Well, there are 6 110 planes in any cubic structure. But only in BCC are those the close packed planes. Make sense? Okay. So that means 2 directions per close packed plane, 6 close packed planes. There are 12 what we will call primary slip systems. That is, there are 12 possible ways in which a BCC lattice is equally likely to deform. Equally and most likely to deform. Okay? Does that make, everybody kind of see that? So there are 12 primary slip systems in BCC. So now, let's see if you guys can figure out what it is for FCC. So let me draw FCC up here. Okay, those are all that's the FCC. What is the close packed plane in FCC, yes?
The faces, so like, I don't know
The
how.
face?
I don't know which ones to say that would be, but I'm just gonna be all the faces, because they're all.
100.
So the 100 would be the face. That is, however, not the close packed direction, or close packed plane.
Oh, right, isn't it
What do you say?
111.
The 111. Right, the 111, I'll just draw it in red again on this one. The 111 intersects each axis at 1, so it is this plane.
Oh, it's a triangle.
Right? And if I looked at that plane just in hard sphere model just by itself, I would see this. That is the close packed plane, because that's where all the atoms touch each other. Okay? On the faces, these three form a face. Right? So on the face, I still have that, but then this and this, right? There's a lot of space between the corners. That's not as dense as the 1, 1, 1. So the close packed plane is the 1, 1, 1. How many close packed planes are there in the FCC cell? How many do you see in there? You see 6?
Wait,
Well, there's
Just give me a
two
second.
right here, because there's one parallel to that lane.
12. 12.
12 planes?
24.
36.
2048.
2048.
Okay, so there's one.
24.
That's my guess.
It's just another one.
It's like 24 acres.
There's more than one.
There's 3 other corners you can connect.
Alright, so I can do the other 3 corners. I
consecutive
can do
years in a row.
this corner right here. I can do this. Right? I can
Over
do
9,000.
the front corner. Which is different, right? Those two are not the same, those are not parallel. And I can do this corner. Wait, where's my flag? I can see, kind of see the black and the blue are different, right? Turns out that's it.
Really?
Because if I connect, if I now come in here and connect this, and this, and this, see that one? That one's parallel to the other one. So essentially, you can kind of see it. You can see it from the side here. If I'm working from this corner, this is a 1, 1, 1 plane, and then there's this black one that's a 1, 1, 1 plane, and then this black one is parallel to that black one. I'm kind of looking almost edge on the black 1, 1, 1s. So there are actually 4 close packed planes in the FCC structure. How many close packed directions do I have in each plane? 3. 1, 2, 3. Everybody knows the reference?
The world may never know.
What are those directions? What family of directions are those? They're the 1, 1, 0 family of directions. Face diagonals. Right? So 1 in the X, 1 in the Y, 0 in the Z, that gives me that face diagonal. And there are 3 of those per close packed plane, for again, 12 primary slip systems.
Wait, so, oh right, because each edge of the plane, each edge of those planes is a face diagonal.
Each edge of those planes is face diagonal. Of those triangle, you mean the triangle planes?
Yeah.
Right. Yes.
Is every single set going to have 12 primary subsystems?
It is not. Go on to another example after this. Let's do hexagonal. This is the one that's hardest for me to draw, but you know.
He chooses you.
You're just a problem, so I volunteer you to tribute.
Okay. On drawing the atoms. Okay, here's hexagonal. What's the close packed plane in the hexagonal structure? I've drawn the whole thing. In reality, right, this is the unit cell, right?
We draw the lines of the unit cell, its own diagram,
Okay,
maybe.
I'll do them in, how about I do them in red? So here's the real unit cell.
And that's got one atom in the middle of it, right?
And there's one atom, that's what this thing right here is sitting in the middle of it. I'll draw that maybe in red so you can see what it's saying. That one's in the middle. So, what is the close packed plane? Or the family of close packed planes? What's that?
110?
Got 110, what'd you say?
I was just asking, is this like the HIJK?
No, we use HIJ, that's why I went ahead and drew the, or you know, we would or use HKL.
Yeah.
HKL. So that's why I went and drew the red. So drew the HKL in the red system, because the others were redundant. So I got to vote for 110 for the close packed plane. What plane is it? Can you tell me what the close packed plane is qualitatively?
The,
Is it the edge?
So the edge is not a plane.
It's the
The face, the body diagonal, the top, the bottom, you know. What kind of, what's the structure of a close packed plane?
So like all of them form one.
Triangles.
form.
Triangles. Tetrahedral.
A little more.
Triodontal. Oh, they're hexagons.
The close packed planes are the ones that are arranged like hexagons.
Oh.
What planes are arranged like hexagons here?
The
Face.
Right, the top and the bottom.
1, 0,
Right? So what is the top and the bottom?
1, 1,
It is not 110.
0, 0, 0, 0.
It's not 0, there's no such thing as 0, 0, 0. 0, 0, 1. Right, so the direction that is perpendicular to those planes has the same coordinates or whatever, same three numbers as the plane. And the direction perpendicular to those is 0 in the A, 0 in the B, 1 in the C. The vertical line is perpendicular to those planes, 0, 0, 1 is the plane. How many of those planes are there?
3.
Remember, if they're the same thing parallel to each other, they're not unique.
Oh.
There's only one. Only one close packed plane. That horizontal layer. How many what's a close packed direction?
110.
Well, it turns out, actually, no.
1, 0, 0.
100. Because in reality, these are actually defined from this point. So 110 would be that direction. If they were defined from here, then 110 would be
That's what I was
right. But when you use the red lattice, you start from the sharp corner. That's the definition of the origin.
So,
So 100 is
So that's
this
the
or that. But 1, 0, 0 and 0, 1, 0 are the same. Because A and B are interchangeable.
Why wouldn't it be a diagonal across that face?
This one?
Yeah.
It is, it's just.
Because this body diagonal is in there, right? That's part of the same family. This is the direct, this is the 1, 0, 0. Right? That would be the 0, 1 bar 0, for instance. Right? This one right here would be the 0, would be the 1, 1.
1,
The
1,
0. What's that?
1, 1 bar 0.
1, 1.
That's how you do that.
Yeah, 1, 1 bar 0, right. 1, 1 bar 0. Right. And 1, 1 bar 0 is different than 1, 1, 0 in the hexagonal close back.
Yeah, but why is it this 1, 0, 0 instead of 1, instead of?
It's that family, the 1, 0, 0 family.
So all three of those fit.
I'm just saying, like, when you look at the hexagon that you drew, that's behind you, would it be across those three? Which is
So,
the diagonal?
from the hexagon, this is my origin, this is A, and this is B. So 1, 0, 0, and 0, 1, 0 are the same, or, oh, sorry, 0, 1 bar 0 are the same, and 1, 0, 1 bar would be, actually that would be this angle right here, this direction right here, is going to be 1 bar 1, 0, actually. But anyway, the point is, it's a triangular ones, right? The ones where the things touch. The close back directions are the ones they touch. How many close back directions are there in the close back plane?
3 or 6.
There are 3. Right? 'Cause I can only, those are the 3. Those 3 triangles, so that triangle covers all 3. Any other direction would be a parallel duplicate of those. So there are 3 per close packed plane, for a total of only 3 slip systems, primary slip systems. The reason for that, even though both of these are fully densely packed, the reason for that is because these 3 in the center have a different orientation, but the top and the bottom have the same. So it's the A, B, you know, the A, B, A, B, A, B, or it could be A, B, A, C, A, B, A, right? But there's an A every other one. Here, we have A, B, C, A, B, C, A, B, C as we stack them. And so we can actually get a direction of propagation across those planes. Right? So we have that back face, we have an A, B, C configuration where the atoms line up and make another close packed plane in another close packed direction. Here, we can't do that because we have the A, B, A, B, A, B structure. So the hexagonal system only has 3 slip systems. The base center cubic and body center cubic both have 12. Oh, wow. Okay. I'd do simple cubic, but we haven't gotten there yet, so you guys can probably figure out simple cubic on your own. Just out of curiosity, see if anybody can quickly identify for simple cubic, what's going to be the close packed plane for simple cubic?
1, 0, 0.
Right, the faces for simple cubic. Right, the 1, 0, 0. Right, so the one, I'm sorry, no, I asked for the plane first. What is the plane? What's the plane? What's the close packed plane in simple cubic?
0, 0, 1. No.
So, what's that? So it'd be I was looking for qualitatively, the faces, right?
Yeah.
The faces are the close packed one. What is the close packed direction?
The edges of the.
The edges, right. So how many close packed planes do I have here?
3.
I have 3 because the top and the bottom are redundant. Right, so there are 3 close packed planes. And how many directions per? What are the directions put in, what would I put in here? actually be 0, 1, 0 if I were going to be consistent, because the 1, 0, 0 direction does not lie in the 1, 0, 0 plane. Right, the 0, 1, 0 direction lies in the 1, 0, 0 plane. How many of those directions per plane? 2. I can go vertically, or I can go horizontally. 2 per plane, for a total of 6 slip systems. Everybody see it? Hopefully. Okay, and then we'll talk later about how we, next time, about how we start to figure out which slip systems are going to be active. In other words, just because they're all equal doesn't mean that they're all equally likely to occur. Question?